Alright, welcome to our fifth video of Unit 3, Chemical Bonds. There are three main types of bonds that elements can form: ionic bonds, metallic bonds, and covalent bonds. Hopefully you've heard of these three before. You've probably mainly just heard about ionic and covalent, maybe not much metallic. By the end of this unit, though, you will definitely know quite a bit about each of these three bonds. First off, let's talk about ionic bonds. These are formed when electrons are transferred from one atom to another. Thus, we form a cation anion. For example, we take this electron, move it to chlorine. Now, we don't have one in sodium. We actually get rid of that whole shell. And we have two extra in chlorine. We form a cation of sodium and a chloride anion. The result from an ionic bond is typically called a salt, which is partially why we tend to call it NaCl, sodium chloride. And this commonly occurs between a metal and a nonmetal. For example, metal, nonmetal, metal, nonmetal. Typically what you find is you will have the cations surrounded by the anions, which are surrounded by cations, and it forms a very strong bond. Metallic bonds are less common. They occur when two metals bond together. But in a metallic bond, instead of electrons being transferred, they are actually shared amongst all the atoms in the compound. This forms what we call a sea of electrons. These electrons now surround all the positive metal ions. So all these were originally gold, and they are positive because they gave up their electrons. The electrons are now kind of floating outside, and they can move however they wish, which is partially why metals can conduct electricity very well, because the electrons can just flow right through the compound. And that is a metallic bond. A covalent bond is where we're going to spend most of our time in this unit. Covalent bonds formed when electrons are shared between two atoms. And the result from a covalent bond is called a molecule. Commonly, this occurs between a nonmetal and another nonmetal. So notice our sharing. If we share between two hydrogen atoms, they both are touching the two hydrogen atoms. Two fluorine atoms, and we get two fluorine, them being shared. Two oxygen and a carbon gets a CO2, but notice these four are between both of them, and these four are between both of them. And four fluorine and a carbon, we get CF4, and each of them are sharing a total of 2 electrons. And that is a covalent bond. When covalent bonds form, the electronegativities of the bond are often different, and thus we share electrons. They're not shared equally. For example, we have what's called a nonpolar bond, which is when they are actually shared equally. And you'll notice that most of the shape it's kind of even. It's evenly distributed around both atoms. For an ionic bond, they're not overlapping at all because the electron is completely transferred. For a polar covalent bond, which is what we're about to talk about, notice that the bigger shape is around chlorine. This represents chlorine having a stronger pull on the hydrogen. Hopefully you remember electrons are all the time moving around. This says that most of the time they'll be around chlorine as opposed to hydrogen because chlorine has a higher electronegativity. So if the electrons are shared equally, which is commonly when both atoms are the same element, we call it a nonpolar bond. For example, two fluorines are nonpolar. Again, this represents their electron cloud, and they kind of merge. And it's pretty equal around both of them. A polar bond is when it's unequal. Typically, anytime you have a bond between two different atoms, or two atoms of different elements. So you're bonding two atoms, and both of them are a different element. It'll be polar, because they'll have different electronegativities. One will be stronger, and will take more of the electrons, forming a kind of partial negative charge. And one will sort of be losing them a bit, forming a partial positive charge. Ionic bonds occur when the electronegativities, however, are so different that one actually takes the electrons instead of just sharing, like with metals and nonmetals. But again, we're focusing more on the covalent bonds. So here's an actual chart that gives us a picture of really the different electronegativity differences we can have. I've given you a chart about that using electronegativities, or if you're watching this online, you can just Google electronegativity chart or just wait till tomorrow. Basically, every element will have an actual electronegativity value. And all you do is take the two values of the elements, subtract the bigger from the... See ya! That was Coach Chris heading home, which is... I'm just going to leave that in the video. You take the smaller one, subtract it from the larger. If they're the same value, it's a non-polar covalent. Remember, they're shared completely. If it's between 0 and 2.1, that's polar covalent. So they're sharing, but one's starting to pull them a bit more. And if you have greater than 2.1, one pulls strong enough to rip it apart, and you have an ionic bond. I don't really know why a 2.1, but that's just the value we got to use. So yeah, that's electronegativity and stuff, and Coach Chris. Alright, so now we have a few examples we'd like to make. I'm going to show you one, I'm going to let you try the others, but I'm going to tell you there are two ways to do this. The first is by using our chart, and that is the way I'd like you to do for these. But if you don't have your chart, there's another way to do this. There are a few times where the ways may conflict, mainly if you start working with transition metals. Most of the time we won't be using transition metals. So the second way I teach you, which is a lot easier, will work. But I just want to explain why the chart method is used. So first off, H and F. On our chart, H has an electronegativity value of 2.1, and F has a value of 4.0. The difference between those is 1.9. That means this is a polar covalent molecule, or bond. That's all you do. So 4.0 minus 2.1. And I'd like you to pause the video and try and find the others. You're just finding the difference and figuring out where they are on the chart. So yeah, have fun. Okay, welcome back. And we're going to start working. So ClCl, actually I'm going to erase that. ClCl, they both have values of 3.0. 3.3, 3.0 minus 3.0 is 0. That means nonpolar covalent. Please keep in mind that I do want both of these words, not just nonpolar, not just covalent. They both are quite important, and yes, if you have one, I will mark you wrong if you don't have the other. All right, NaCl. Now, here's where it gets a bit weird. Na has 0.9 and Cl 3.0. Oh, I'm sorry, I was thinking of a different example. So 3.0 minus 0.9 is 2.1. That's going to be ionic. Here's the weird thing, though. Our chart does say, it talks about being less than or greater than ionic. If it's 2.1, it's kind of your choice to pick. But in that case, you want to look at the types of elements. Because sodium's a metal, chlorine's a non-metal. Typically, that'll be ionic. But in this case, so that's why in this case I'm saying ionic as opposed to polar covalent. Okay, for HO, H is 2.1, O is 3.5. 3.5 minus 2.1 gets you 1.4. This will be polar covalent, which, by the way, should make sense. They're both nonmetals, but they're different nonmetals, so covalent but polar. And lastly, CuF3, or Fe. Cu has 1.9. Fe has 1.8. Take those difference, you get 0.1. That means this should be a polar covalent. Now I'm hoping you're thinking, wait a second. Because this is where the chart sometimes doesn't make sense, like I said, when you use transition metals. Because hopefully you notice, copper and iron are metals. The only bond that I told you that uses both metals is metallic. Which means, in this case, we really wouldn't want to use the chart. So I'm going to redo the other ones. This will end up being metallic, and let me show you how I normally do this. I wanted to show you the chart. You don't normally have to use the chart, but technically when it comes down to it, you want to go with the other way that I have. I just wanted to show you how to use the chart. So You ready for the easier way? All right, H and F. They are both nonmetals, but they are different nonmetals, polar, covalent. Cl and Cl are both nonmetals. They are the same nonmetal, so nonpolar covalent. A lot faster, isn't it? Na and Cl, metal, nonmetal, ionic. HO, two nonmetals. They're different nonmetals, polar covalent. And lastly, two metals, metallic. So you're probably thinking, wait a second, Mr. Booth, why didn't you just show us this method in the first place? To be honest, next year, I'm probably just going to use this method. My intention was to show you an alternate method, but as I've gone through most of these problems, the method I just right now showed you is what I tend to use, so there's not much reason to teach you a second way. Stay with the chart. That way, if you're given that, you know what to do with them. Next year, I probably won't teach them the first method. So on your test, feel free to do this way. Don't worry about the chart unless they specifically ask it. So let's move on. So in general, the larger the electronegativity difference, the stronger the bond. Now, this is an indication of like different types of strong bonds, which we'll get there in just a bit. But the stronger the bond, the closer the atoms will be pulled. I mean, think about it. If you're playing like tug of war or something and you're both really strong, well, and one team's strong, you can pull them closer. If you're, I can't really think of another idea. For example, that's a single bond, double and triple. The triple is the strongest. These are actually representing the lengths, and you can tell that they get shorter with the stronger bond. So, in addition, the stronger the bond, the more energy it'll break. This is just a picture of ropes. But think about it, it's a lot harder to break this rope than it would be to break this rope. All of it's kind of hard, but this one's definitely a lot harder. So the same concept works for bonds. So finally, sometimes a single bond will not be enough to satisfy the octet when we're about to start doing Lewis structures. So you may need a stronger bond, and that's okay. Just wanted to tell you these with single dashes are going to be called single bonds. Double bonds are when you've got two lines. That represents two pairs of electrons for a total of 4 electrons being shared. And triple bonds are 3 lines representing 3 pairs for a total of 6 electrons. So we're about to start Lewis structures, and I just want to give you a little terminology before that. And as kind of a summary, if you will, a triple bond is shorter and stronger than a double bond, which is shorter and stronger than a single bond. So there you go. That's chemical bonds. All right, and for our practice for this section, I'd like you to make 5 pairs of atoms and tell me what bonds they will have. Meaning, pick total of 10 atoms, or actually at least 5 when it comes down to it. 5 pairs. Now, my requirement is that at least one of those pairs needs to be ionic, one of them needs to be polar covalent, and at least one needs to be nonpolar. The last 2, I don't care, but I want you to basically pick 2 atoms, so they'll be ionic, 2 that'll be polar covalent, 2 that'll be nonpolar, and I really don't care about the others. So keep in mind that just the different properties of them, and that's what you're doing.